Okay, well, it's 1:01, so even as people trickle in, let's get started. Good afternoon. Welcome to the Penn State CTSI BERD seminar series. BERD stands for Biostats, Epidemiology, Research Design. And this is, we're getting close to the end of our fall series. I'm going to go through a few, we are recording, so we ask folks to keep your microphones muted, but I'm going to go through a few ground rules. First of all, this series is co-hosted by myself, Terry Murphy, as well as Professor Lan Kong and Associate Professor Jay Ju. All of us work in the Division of Biostats and Bioinformatics as part of the Department of Public Health Sciences here at the Penn State College of Medicine. Here is the list of seminars that we've put on and continue putting on this fall. You see we're at the second last one down here in bold. Today, we're going to hear about basic principles of study design from Alan Kunselman. And then on December 9th, we'll have our last talk of the fall semester, which will be considerations of diversity, equity, integrity, and belonging in clinical research. Here are a few of the rules. We are recording this session. Please mute your microphone when our speaker is giving his lecture today. Please feel free to submit questions on the chat box during the lecture, and I will be monitoring the questions, but our presenter today has expressed a preference to answer them after he's finished. Note that everyone who registers will receive the slides, a link to view the video of this presentation, and seminar feedback survey. And we ask you to kindly take a minute or 2 minutes to complete the seminar feedback, as it's very useful to us. Today's talk is called Basic Principles of Study Design. And we are very, very pleased and fortunate to have Alan Kunselman with us today. He is a biostatistician in the Department of Public Health Sciences here at the Penn State College of Medicine. He has been directing our biostatistical consulting service for the past, since 2005, so for a full 20 years. He supervises non-faculty level biostatisticians, and he is a very experienced applied biostatistician with wide-ranging areas of application. He has worked on studies including polycystic ovary syndrome, infertility, cardiovascular disease, obesity, and pediatric research. He has been extremely prolific in co-authoring more than 275 peer-reviewed publications with over 11,000 citations over the years. He's actually been here at Penn State since 1995. So he's been with us for 30 years and has accumulated a vast wealth of experience. So I am delighted to hand the floor over to Mr. Kunselman, and Alan, you can take it away.
Thank you, Terry. Let me share my slides here in a second. Just want to confirm everybody can see the slides?
Yes, look great.
Okay. Thank you for the introduction, Terry. I just want to go through the outline today. This is not going to be a very detailed talk, meaning formulas and numbers and things like that. This is more of an overview and a thought process. So the outline today, we're going to talk about types of non-experimental and experimental study designs, the strengths and limitations of these study designs, what is the best study design by goal, and then some clinical trial study design and planning considerations. And you will have the slides, as Terry mentioned, after the talk. The last topic may be cut a little short given time, but you'll have the slides to refer to if you're interested. So I wanted to start this talk by just giving some basic quotes. And the first one's from a statistician named Pocock, who said, "A clinical trial is any form of planned experiment which involves patients and is designed to elucidate the most appropriate treatment of future patients with a given medical condition." Simon has a quote, "The guiding principle of clinical trials is to ask an important question and get a reliable answer." So in general, study design is a scientific method that a researcher follows to assess the association between an exposure and an outcome. So I want to talk about two basic sets of study designs: non-experimental or observational studies and experimental studies. The non-experimental studies, this is where you observe both the exposure and the outcome, as opposed to an experimental study where you assign an exposure but observe the outcome. So what are some types of study designs here? Well, a non-experimental study or observational study, you can think of case report, case series, a cross-sectional study, a case control study, and a cohort study, where a cohort study can be prospective or retrospective. And just so you know, this is just overalls. There are also specific types of these experiments. Some of you may have heard like a nested case control study, which is like a combination of a case control study and a cohort study. But I just want to give a general overview of the main topics, not get into the nuance of specific design. And then you have the experimental study, and the gold standard here is basically a randomized clinical trial. And a design, you could have a parallel design, a crossover design, a factorial design, and there are other types of designs within a randomized clinical trial. So let's start about talking about the non-experimental studies and ones that are just descriptive only. So the main objective of the research is to describe the main features of the population. And types of studies here are case report, which documents an unusual medical occurrence that may represent the first clue in the identification of the new disease or an adverse effect of exposures based on one patient. And some things about a case report: there's no control for the exposure of the assignment, the endpoint ascertainment, or confounders. There is not a control group for a case report, and it's susceptible to large selection bias. So a case series, all of that is a collection of case reports. So it's more than one subject. And it's more weight than a case report, but again, it's susceptible to large selection bias, as it's just a collection of a few specific case reports. Another type of non-experimental descriptive study is a cross-sectional study. And this is a study where data is collected at one point in time or a relatively short period of time and reflects information of prevalence of the outcomes. So what you do is you assess exposure and outcome simultaneously in a defined population. And we'll talk about, let's get into it, the limitations and advantages of these types of designs in a minute. Now, what about observational analytical studies? Well, the main objective is beyond descriptive, where a specific association is being assessed. And types of designs here are a case control. And this is where a study where the participants are recruited based on their outcome status. So it's possibly a group having the disease of interest and another group that does not have the disease of interest. And information on past exposure is collected and compared between these two groups. A cohort study is a study where their participants are recruited based on their exposure status, not their outcome status. So it's a group having the exposure of interest and another group that does not have the exposure of interest. And for a prospective cohort study, participants are followed over time to observe whether the occurrence of the outcome in both groups. And for a retrospective cohort, it's the same idea. Again, the participants are selected based on their exposure status, but both the exposure and the outcome data have already been collected and exist in the past. So you can think of like a big database where both the exposure and the outcomes are in there. And so what are some examples to get data for a non-experimental observational database? And again, you can think a lot of these are retrospective studies. So you can look at the electronic health record, which has detailed patient data from healthcare providers. You can look at administrative claims data. So these insurance claims data providing diagnosis, treatment, and outcomes. And these can be very large data sets, like millions upon millions of records. You can look at national surveys. If anybody here is familiar with NHANES, so these are large population-based surveys that you can access to answer questions. And disease registries, like cancer registries, can be used to look at observational databases. So on to an experimental study. So what's the experimental study? Well, here the researcher assigns different exposures to participants, possibly based on multiple criteria, and usually in some random fashion, and observes what the outcome. So the researcher is actively carrying out an experiment on the participants. And again, the main type of study here is a randomized clinical trial. So now that I've introduced you to these different types of study designs, experimental and non-experimental, let's talk about some strengths and weaknesses. So what are some cross-sectional study strengths? Well, they're relatively easy to conduct because they involve identifying a group of subjects, collecting information on them, and then analyzing the data. It's a study that can be done in a very short period of time, so there's no worry about following up needed on the patients. There are typically no ethical issues, and that is because the data has been usually been collected, or it's a very short period of time. And again, it's an observational study. So since we're not assigning them a treatment or any intervention, there's usually no ethical or harm being done to these patients, or possible harm. So we have data in all variables. You have the exposure data, the outcome data, confounders are all collected at one point in time. So prevalence may be assessed for all factors being studied. And I'll talk about this later. This is a main point of cross-sectional studies. Prevalence, if your goal was prevalence of a disease, a cross-sectional study is a very good study to follow. You can look at multiple exposures and the outcomes can be studied. So again, you're collecting all kinds of data at this one point in time and seeing, hey, how does this exposure affect these outcomes? Prevalence of disease or other health-related characteristics may be used to assess the burden of disease in a specified population for planning and allocating health resources. So again, once we know what the prevalence is it worth pursuing further? And they're good for providing descriptive results for generating hypotheses for future studies. So again, they're relatively cheap study to do. You can find good information and decide whether, hey, should we look at a prospective trial in these studies? But what are some limitations of a cross-sectional study? Now, one of the big ones is you can't make causal inference. So the time sequence of the exposure and the outcome is not implicated in the design of the study. So it makes it difficult to determine which one came first. You're going in, collecting your data at one point in time or a short period of time. What came first, the exposure or the outcome? Sometimes the exposure may come before the outcome, sometimes vice versa. So you just don't know because it's such a short period of time. They're not suitable for rare diseases. So again, you're going in at one point in time. You wouldn't want to do a cross-sectional study if the disease is rare, because chances are you're going to find 0 cases or 1 case or 2 cases, just a very small number. Incidence of a disease can't be estimated. Again, you're going in at one point in time, so you're not really following over time to get a rate for an incidence. They're susceptible to selection bias because of the sampling and low response rate. So if you're going in and doing a survey for a cross-sectional study, your response rate may be very low, so you might have bias there that you have to account for. They're susceptible to information bias. So recall bias is, these patients come in, you're going to ask them what happened in the past, and they may not recall well. You can have non-response bias. Again, back to surveys, you may get people not responding, or you can have errors in measurement. And they're also susceptible to confounding bias due to the inability to collect information on all potential confounders. You may not know what all confounders may possibly be, or you may not have the money to collect all the potential confounders to study. So what are some case control strengths? Well, they're fast to be conducted. There's no follow-up needed, as both the exposure and the outcome have already occurred. You already have that data collected. They're typically low financial cost, as the data is collected in a relatively short period of time, no follow-up needed. They're typically, oh, I went backwards, sorry, apologize. Cohort strengths, that's where I wanted to go. No, sorry, case control. Back to case control strength, got ahead of myself. No ethical issues. Again, you have the data. The appropriate studying rare diseases because participants are selected based on the outcome status. So here's the case control. You're selecting this participants based on their outcome. Are you a case or control? So they're appropriate for studying disease outbreaks. Quick example would be, say people go to a restaurant and a certain number of people become sick. Well, then you go to that restaurant, the sick people are your cases, the people that didn't get sick are your controls. And then you look back in time to see, okay, what food did they eat that possibly could have made them sick? And they're appropriate for assessing the association between multiple risk factors and one outcome. So again, the outcome for a case control study is whether it's a case or control. You go back in time, see possible risk factors, and you can assess many risk factors. Oh, is age related to my outcome of interest? Is whether they have hypertension related to my outcome of interest? Is whether they're a smoker related to my outcome of interest? Where the outcome of interest is, are they a case or a control? What are some limitations of a case control study? Well, they're prone to selection bias if the cases or controls cannot be representative of the underlying population. They're prone to information bias because information collected has happened long in the past. Again, you have recall bias and errors in measurement. Confounding may be an issue, as it might not be feasible to collect information on a wide range of potentially confounding variables. Again, you may be limited by cost or time. They're not appropriate for studying rare exposures, as you're likely not to have enough subjects to be found and what will be exposed. And you can't make causal inference. How about cohort studies? What are some strengths of those? They're kind of an in-between case. They're less costly and easier than experimental studies. So there still is cost associated with any study, but cohort studies are typically more expensive than a case control study, but they're usually much cheaper than doing an experimental study. They directly measure disease incidence due to follow-up. So if your primary goal is incidence of disease, a cohort study is a design you should follow. Temporal relationships can establish between exposure and outcome, helps your building evidence for causality. They're appropriate for assessing the association between one exposure and multiple outcomes. So again, how you select your participants for a cohort study is, what is the exposure? You select people that are exposed and not exposed. For example, are you a current smoker? Yes, no. Follow them over time, but then you look at multiple outcomes in that, is smoking status associated with lung cancer? Is smoking status associated with developing diabetes? Is a smoking status associated with developing any other type of disease you may be interested in? So it's basically the reverse of the case control study. And they're appropriate for studying rare exposures. Why? Just like case control studies are good for rare diseases, cohort studies are good for looking at rare exposures. And they're fast to be completed because it's in a retrospective cohort study. So if all the data has already been collected, the exposure and the outcome, they're a very fast study to do. What are some limitations? Well, they do have expenses to them. And it can take a long period of time, especially if you're doing a prospective cohort study. For example, you may say, oh, are you a current smoker? We're going to follow these participants over 10 years to see if they develop any kind of cancer. Imbalances in subject characteristics could exist, so you could introduce bias. They're affected by confounding because it may not be feasible to collect all information on potential confounders. They're not appropriate for studying rare outcomes. And loss to follow-up, especially when the duration is very long, may introduce some selection bias. So let's move on to the experimental studies. Well, why would you want to do an experimental trial? Well, here the treatments are compared directly to establish superiority. And the big thing, the randomized controlled trial is basically the gold standard for causal inference. It's the strongest empirical evidence for the treatment efficacy. You can randomize participants, which minimizes allocation bias and selection bias. You can use blinding or masking methods to minimize performance bias. You can use double blinding to minimize assessment bias. Prospective design minimizes recall error and selection bias because you have active, ongoing communication with the participants. Randomization minimizes confounding due to unequal distribution of prognostic factors. And randomization makes groups comparable according to both known and unknown factors. So a big thing with randomization, it kind of balances your groups out so you don't have to worry so much about prognostic factors and confounders. But if you know that there's a very strong confounder with your outcome of interest, you can do a stratified randomization, and this makes these group comparables with known confounders. And again, they're considered the gold standard for publication of any causal inference you want to make. But what are some limitations? The biggest, well, there's a lot of limitations, but one of the biggest is they're very expensive studies to do. A lot of times you have to hire a lot of personnel. You need people to help recruit. You need nursing a lot of times. You need biostatisticians and other researchers. So they can be very expensive to do. It can be very hard to find and recruit participants. A lot of people don't want to be a guinea pig in your experiment. Recruiting participants can be a very long, time-consuming process. You may go into a study thinking, oh, I can recruit 5 people a month, and then you find out you can get 1 or 2 a month. So it can take a long time. There's greater responsibility in documentation, especially if you have an NIH grant. You have to do a lot of documenting, reporting to the different institutions, reporting to the IRB when you have adverse events, reporting to your study sponsor when you have adverse events. So it's pretty meticulous on documentation. They typically require multiple visits over time, which adds up to cost and length of the trial. A long trial time may result in the loss of relevance, as clinical practice may have moved on by the time you publish. So again, if you're doing a long clinical trial, something new may have come up in the interim, and you kind of lost your window, and what you started out really isn't relevant anymore. A randomization requires clinical equipoise, ethical issues. Is it really ethical to assign patients to a placebo? In most cases it is, but in certain cases it's not. Participants may drop out, may be an issue, especially for long trials, and participant compliance with the protocol can be a big issue. So what's the best study design for the goal that you're trying to do? Well, if your goal of the study is to estimate prevalence, the design I would recommend would be a cross-sectional study. Sometimes you can do it with a cohort, but a cross-sectional is a good, relatively cheap study to do to get prevalence. What if you want to estimate the incidence of a disease? A cohort study is the best case to follow there. Sometimes you can do it with an RCT. What if you want to prove causality, or at least attempt to prove causality? A randomized controlled trial is the gold standard there. And these last two, generalizability and feasibility, basically any trial can address these issues, and it really depends what the goal is. For example, for feasibility, if your goal of the feasibility is, can I recruit patients fast enough to actually do a big trial? You may want to do a pilot study to see how many patients per month you can actually get in a small scale study to see, oh yes, it's feasible or not to go on to a larger study. So now that we're on to basically in general, what are some clinical trial? This portion of the talk is going to be mostly what are some things we can think about or plan for before we start the study to make sure we get a good design going. So what are some components? Well, a question which has a potential for influencing medical practice. It uses a control treatment that's widely accepted. It uses an experimental treatment that's widely applicable. It uses an endpoint as a direct measure of patient benefit, for example, survival, quality of life, and it studies a group of patients who are broadly representative. So what are some components of a reliable answer for this study? Well, can we randomize the treatment assignments? Again, this is a prospective RCT. So as I mentioned before, this helps minimize a lot of like selection bias and other types of biases. Is the sample size adequate to address the question? Do you have enough power to answer your question? Do an intention to treat analysis, meaning use all the data available to avoid biases when you look at completers only. And testing an a priori hypothesis on mature data, which means if you're going to do interim analysis, you need to account for them in your study design, power calculations, and other parts of the study. What about some design considerations for a clinical trial? Well, how do we get our controls? So you want to control the outside influence or appropriate comparisons. So compare the experimental treatment to a placebo or standard therapy to account for what we call sometimes the placebo effect. And there are different types of controls. The first is one that I do not recommend at all, but it is done from time to time, which are historical or non-concurrent controls. And the reason I'm not recommending is they're done at different times by different investigators, different protocols, possibly diagnosis methods. There's a lot of biases here, but what it essentially is, in this little diagram I have here, think of C as your control group and E as your experimental group. So what you're doing is you're treating everybody on some treatment and comparing to some historical control. For example, pull data from a paper published 10 years ago and see if your treatment, is it different than what was published 10 years ago? Or another group that was collected a long time ago. A better design for controls are concurrent controls. So this can be done like a parallel study design. So if you think about a randomized control trial, you could randomize people to your control experiment and your experimental treatment, and then follow them over time. So that way, everybody's under the same protocol, the same study design, the same investigators. So we're all good there. Another type of study is self-controls. So you can think of this as like a pre-post study. For example, say you want to do a survey and you had people come in, you gave everybody a survey, your baseline survey, and then you do some intervention, like changing your teaching methodology. Then after that intervention, you give everybody a follow-up survey and then compare the pre and post. That's a common design, pre-post designs, but one problem with them, the time effects confounded with the treatment. Another type of trial you can think about would be a crossover design, and this includes self-controls and concurrent controls in an efficient design, and it requires a washout period. So essentially, if you think about a randomized control trial, you can randomize patients to a sequence of half the group to get the experimental treatment and then cross over to the control treatment. And the other half gets a sequence. They're going to start off with the controls and cross over to the experimental treatment. And by washout period, let's assume that the intervention you're doing is a drug. So you might want to know what the half-life of that drug is. So you want to have that washed completely out before you start the second phase of the study. Quick example would be, say you started a study, it's a 6-week trial on phase 1, and then the washout period is 2 weeks. So after 6 weeks, After that 6 weeks, nobody gets any drug at all. They wash out. And then you start up 2 weeks later for another 6-week follow-up where people cross over. Another type of study design to think about is a factorial design. And this is a trial which participants are randomized into 2 or more intervention groups. For example, we could have, if we had 2 treatments, treatment A and B, you can randomize people to treatment A only, treatment B only, subjects that get both treatment A and B, and then subjects that get neither treatment A nor treatment B. And if you're familiar with clinical trials, you may have heard the term like double blind, double dummy. This would be a case where it'd be like a double dummy, where we call the dummy like the placebo group. So a double dummy would be one group would get a placebo treatment A, and the other group and a placebo treatment B. Treatment A only would get active treatment A and placebo B. Treatment B only would get active treatment B, but placebo A. And of course, both A and B means people would get both the active treatments. So how do we select our groups? Well, again, we have our active intervention group or our experimental group, and we want to compare it to what? A lot of times you have a placebo group, so it's no active intervention. Or you can compare your experimental group to a standard or usual care, or you can compare it to an active control, which is an already known effective intervention. So what do we do when we compare it to placebo group? Well, you want to use a placebo if there's no standard intervention, or if the standard intervention, but there's very low risk of not providing it to the participants. And one issue with the placebo group is it's ethical. Sometimes you may not, is it really ethical to give people with a disease a placebo, which you know is not going to help them? So what about when we look at standard of care or active control comparison groups? Well, some of the issues here come in, there's many candidate interventions. There can be strong evidence rarely exists to guide the selection of the intervention. What dose or intensity are uncertain. So let's assume that our experimental, we're going to give people a drug. An experimental drug is going to be 10 milligrams of the experimental drug. What dose do we use for our active control? Is it still 10 milligrams like the other, or is it one more effective that should be compared to 15 milligrams? So these are always things you need to think about. What intensity and dosage is really a true good comparison to your experimental treatment. Efficacy of standard of care is often not tested, and then there are variations are common. If you're doing a multi-center trial, you say, oh, we want to compare it to standard of care. Well, different providers or clinics could have different quote standards of care. So you have to decide, we have to decide on one standard of care and make it universal across all centers. Another thing to think about when you're designing your study or planning your trial is your study participants. So the goal would be, you have your target population, your accessible population, and your samples. So for example, your target population could be all hospitals in the state of Pennsylvania. Your accessible population may be only hospitals in the Penn State University network. And then from that network, you sample participants to be in your study. So what are some ideal study participants? Well, an ideal accessible population, you want them to have a high risk for disease that you're looking at. You want them to be candidates for the treatment that you're trying to study. And you want to have them be representative of the target population. And also, how feasible is it? Is it feasible to recruit these participants? Is it easy to follow them up? Do you think this group of participants will comply with the protocol you have planned and studied? Are you able to obtain high quality data from this population? And think about participants. What are inclusion and exclusion criteria or characteristics of the population that you want to have in your study? Exclusion criteria can be, what do you want to consider? Compliance with the intervention protocol. follow-up, safety, and ethics. So again, before you do your study, you need to think about what are some inclusion and exclusion criteria that will make this population that I study that is accessible, generalizable to my target population. So what are some common recruitment strategies you can use to get these participants in your trial? Well, this is kind of in the past, but you used to have general mailings to licensed drivers or registered voters. You can do target mailings, for example, to AARP members or other particular groups to target the mailings. You can look at mass media, be it social media like Facebook, Twitter, TikTok, whatever you can get on there. You can do radio ads, TV ads, newspaper and posters and flyers. You can do screening, look at community and workplaces, try to recruit people. One of the best tools for any study is physician referral. If you can get other physicians on board to your study and refer their patients, that is almost the gold standard to get a flow of participants for your study. The medical record reviews, you can look at Trinetics to try to find patients that meet your inclusion-exclusion criteria. And then you look at internet, social networks, do banner ads, look at clinical trial registries, like advertise on clinicaltrials.gov. Some general comments about recruitment. Recruitment begins with the study design. You can have the most elegant, great study design in the world, but if you can't recruit patients to it, it's not going to be useful to anyone. So you really need to think about, what can I get people on board on this study? The response rate is usually lower than expected. Everybody goes in with an idea of, I can recruit 10 patients a month, and in reality, they might get 4 patients a month. So you just really have to temper your expectations and make sure you can recruit for the study. The required resources for a study are usually much more than expected. Hey, do I need to hire a dedicated recruiter? If so, that's an expense and a cost that I didn't factor in, or I need to think about to factor into my budget. Dedicated personnel are necessary. Recruiting patients is not easy. It takes a lot of effort and time. So think about that and budget that in when you do any kind of protocol. Recruitment period is usually longer than you expect. If you think you can finish a study in 2 years, it may take you 3 years. So always be conservative. Identify several recruitment strategies. I just outlined things like newspaper ads, TV ads, which are probably not worth it. But if you go into a study and think, oh, I'm just going to throw up a bunch of flyers, that's probably not enough. You need to have multiple ways to reach out to the community to get people to know about your study and then join the study. And then remonitor and recruit them often. So I mentioned this earlier in the talk, but if you're doing a randomized controlled trial, what's the point of randomizing people? Well, as previously mentioned, the RCT is a strong study design. Its advantages are it avoids selection bias. And selection bias occurs if the allocation process is predictable. I've seen people do this and it's poorly. So why you want things random is, again, you don't know who's going to get the treatment. And this is not random, but a long time ago, I saw somebody try to do this. It was like, well, what if I give treatment A on like a Monday, and then everybody comes in on the next day, Tuesday, or give treatment B, and then go A, B, A, B. It's random. I don't know who's coming in on Monday, Tuesday, Wednesday, but that way they think that's random, but it's not. If you know everybody's going to get treatment A on a Monday, you can tell your friends, hey, there's a good chance you're going to get a placebo on Tuesday, so everybody go Monday to get this treatment. So it's not random that way. A true randomization process, working with a statistician, will help you eliminate any kind of bias there. It produces comparable groups in terms of known and unknown prognostic factors. So again, it minimizes accidental bias or confounding. by randomly putting people in each group in your study. And it adds validity to the stat test you will do at the end of the study. And we're not going to go into this today at all, but there are two main branches of randomization procedures: fixed allocation and adaptive randomization. Well, how does masking or blinding help a study? Well, masking of study treatments so that the assignment is known to various parties involved in the patient management and the data collection during the trial. And the big goal of masking is to prevent personal bias from influencing study outcomes. Again, if a physician knows that patient A is on the active experimental treatment and the study's longitudinal over time, they could at every visit say, hey, how are you feeling? And make sure, putting their bias in, they want to make sure that that active treatment is working. So the levels of masking can be single blind. This is where only the participant is blinded. Everyone else knows the treatment assignment. Double blinds where participant and clinical personnel or outcome assessors are blinded to study treatment, and that prevents assessment bias. And if you can, you want to do double blind at least. And then you also may hear of triple blind, and that includes a blinding the statisticians of the study. So when they're analyzing the data, whoever's analyzing the data, they don't know what treatment A and treatment B are. Everything's just, oh, here's people on group A and here's people on group B. You analyze all the data, come to your conclusions, and then afterward, oh, I found out treatment A was the placebo and treatment B was the active experimental drug. So again, it minimizes bias by the people analyzing the data. You want to think about your study before you start it. How generalizable will the study be to those subjects who meet the eligibility criteria? So things to consider for generalizability is loss to follow-up. What are reasons there's for early withdrawal from the study? What's the potential impact on the study results? Need to consider the compliance with the treatment regimen and routine clinical practice, and maybe lower than the observed in a clinical trial. So again, when you're doing a randomized controlled trial, everything's very controlled. The participants are usually, following the protocol, taking the advice. When you try to generalize this to people outside the trial, they're probably not going to comply near as well as the participants in a trial. Consider how study subjects may differ from the general eligible population. And generalize the source. Consider the inclusion-exclusion criteria. Consider the screen to enrolled ratio if available. Again, if you have to screen 1,000 people to get one person enrolled, your inclusion-exclusion criteria may be way too narrow for the disease, for the population you're trying to generalize to. And any generalizability beyond the source population can be very risky. So what are some more generalization considerations? How efficacy is a treatment, side effects or adverse events, how compliant are the patients on the study, and the ability to assess the progress in routine clinical settings. Another thing to consider when you're starting your study, before you start the study, is baseline data. Again, you want to look at determine what's eligible for the participants. You want to be able to describe the study participants, define any subgroups, and address confounding. So what I'm getting at here is you want to make sure you're collecting all the information you need, have analyzable data at the end, and publish studies. It'd be bad. Almost any study has describe your population. What's the age of my population? What's the gender distribution, etc. If you forget to collect that in your study at the beginning, reviewers are going to come back and say, hey, what is your population? So make sure you're collecting all the baseline data you need to be able to tell reviewers and general audience, here's what I'm defining as our people. You need to think about how are you going to measure adherence and compliance to the study. So you're doing an intervention. For example, is it going to be, if you're supplying some type of drug, Is it pill counts? Is that how you're doing it? Adherence and compliance? If you're doing some sort of group therapy session, what is your goal there for compliance? Is it attending all sessions? Is it, we're going to assume that if a people attend 80% of the sessions, they're going to be compliant for a group therapy session. So you need to think about, how am I going to measure adherence, and what really are my definitions of adherence to this protocol? And then make sure you collect the outcome variables you need. You don't want to do a study and then forget the main outcomes you're looking at. So what are the outcome variables? You have the primary outcome, which is most important variable, which should be clearly stated in the protocol or the manuscript, specified in the primary study hypothesis, and it's what your power sample size estimation should be based on. Define your secondary outcomes. Are they relevant to the research question? How will they be analyzed and reported? And these secondary outcomes are not typically used to power the study. That should be the primary outcome. So what are some desirable features of the outcome? Well, the primary outcome should be clinically relevant, easy to measure, have little measurement error. So random error leads to imprecision, systematic error leads to bias, and should be mask the intention of the assignment or blind to treatment assignment. And back to measurement error. Let's say your main thing in your study is the weight of the participant. You want to have a scale that's very accurate. You don't want to say, oh, this scale's within, it has a measurement error of plus or minus 3 kilograms. That'd be a terrible scale to use for a study. So you want to make sure all your instrumentation is, really precise, that you get good error measurements. What are surrogate outcome variables? Well, a surrogate outcome is usually a lab measurement or a physical sign used as a substitute for a clinical meaningful outcome, which may be very difficult to determine directly. So a lot of times a clinical outcome can be a very expensive outcome to obtain, or sometimes it's impractical or impossible to obtain. So if you can't get the clinical outcome, you want to use a surrogate. And the types of surrogate outcomes, you can have a physiological variable, you can have a clinical risk factor, or a subclinical disease. And so, for example, a surrogate variable could be interleukin markers like IL-1, IL-6, or IL-8, instead of what the outcome of true interest is. So surrogate outcomes typically increase stat power compared to clinical outcomes. And a lot of this because the surrogate outcomes are often continuous measures and measured repeatedly. A lot of times a clinical outcome is binary, like a yes-no outcome. And that's a great outcome. Are you cured, yes or no? But to power a study of a categorical or binary outcome usually takes a lot more patience than a continuous outcome. So a lot of times surrogate measures will be used because it's continuous, and you can have better power because it's continuous, meaning that you can recruit fewer patients in a study. Clinical outcomes are often categorical and may involve surveillance until the outcome occurs. So you may be waiting a long time until a clinical outcome occurs, whereas a surrogate outcome can give you more immediate results and are useful in mechanistic studies. What are some disadvantages of surrogate outcomes? Well, the measurement of surrogate outcomes involve complex technical procedures. So procedures sometimes are new, they can be obsolete, there can be technical or analytic issues. Missing values are often common with surrogate outcomes. Missing values can result in loss to follow-up and poor data quality, and it can lead to potential bias. What are some things to think about before you even start your study is the analytical side. Again, this is where sample size and power calculations come in. A priori, what's the analytical approach? What stat analysis are you going to use? If you're doing a case control study, you do something like logistic regression. If you're doing a randomized clinical trial, you may be using a mixed model or a t-test or logistic regression or other types of things. And Are you going to do intention to treat versus an as treated analysis? I won't go in detail, but intention to treat is you use all data from all patients, regardless of whether it was collected accurately. Here's an example. If people are randomized to treatment A, and if a subject comes in and they're randomized to treatment A, but a nurse accidentally gives them treatment B, you would still analyze that person as getting what they were supposed to get, treatment A, because that's the intention to treat. They were supposed to get A, even though they got the wrong treatment. Versus as treated, which is like a follow-up usually done where, what did the patient actually receive? Oh, they did receive treatment B. We're going to analyze them at what they were as treated as. And for sample size, in a protocol, you should state the assumptions made arriving at the sample size that was targeted for the study. And sample size estimation requires this power analysis. And it usually relates to hypothesis testing and errors. So I'm going to skip ahead in case there's questions on this. Again, I mentioned before, you'll have access to the slides to look at the other things I haven't really talked about to go into. If I'm going to slowly go through the slides here, but we have like hypothesis testing. When you do your power calculation, the big things are type 1 error, which is where you reject the null hypothesis when the actual truth is it's not happening. Type 2 error, you can see, is you don't reject the null hypothesis when in truth that's what's happening. And then you have your 2 correct assumptions. I'll just mention these briefly and then go to questions. So when you think about hypothesis testing in clinical trials, there's basically 3 types you can think of. And probably 99% of the time, you're going to do a superiority study. Here's where the efficacy of treatment E is greater than treatment C. A non-inferiority trial is within a certain margin. You can say the efficacy of treatment E is at least as good as that of an active control or treatment C. An equivalence study is where the margin of efficacy of treatment E is in the same that as an active control. So just quick slides, a superiority study. The top thing is your point estimate. So if you take if you took the difference of your outcome, experimental minus control, and you do a 95% confidence interval, the top thing shows superiority. If nothing happens, if you take E minus C, you'd get 0. So here's a case, the top 2 are superiority shown, and a bottom case where superiority is not shown. A non-inferiority trial is the experimental treatment can actually be worse than your control. It can be worse than placebo, but it can't be, but how much worse? So what you're testing is, you have this thing called delta. How much worse can my control be than my experimental and still be considered non-inferior? And it's just quick graph shows, the top thing shows non-inferiority shown. The 95% confidence interval doesn't cross that red vertical line. And the bottom graph shows it's not shown because it does cross it. And the hardest thing with non-inferiority trials and equivalence trials is determining what that delta is. What is considered non-inferior? Is it 5 units, 10 units, 30 units? That's where it takes expert clinical knowledge and to know what's good there. And equivalence, I'm just showing you the slide quick, just so you have it for future reference. Instead of just a negative delta, you have a positive and a negative delta. So your confidence interval has to fall between those 2. If it crosses that, you don't show equivalence. And this is a big thing that came out of like drug trials for generic drugs. If you're developing a generic drug, you do not want it to be better than the, trying to think of the word here, the drug you're trying to duplicate, and it can't be worse. It has to actually be equivalent to it. So it has to be within those plus or minus bounds. And I'll stop there with these other things. Last thing would be, here's some good references on basic design, these books, and you'll have access slides. Piantadossi is a very good clinical trials book to reference. This time I'll take any questions anybody may have.
Great. Thank you so much, Alan. We do have a couple questions in the chat, so I'm going to start with those. First question. I was under the impression that intent to treat uses entire populations. For example, if the treatment is for diabetes, you use data from all diabetics in the emergency room, regardless of whether they received treatment at all. Then the untreated diabetics serve as a pseudo control group. Is that true, the way this person is describing it?
I'm not typically, when I use intent to treat, usually is in a controlled clinical trial where you're recruiting patients. So you're randomizing people to have active treatment and say placebo. And what that means, everybody's recruited to that trial. Their data is analyzed. So again, I guess in some cases are correct in that if a person's randomized and they never received the treatment, you still would use their data in analysis.
I made a mistake in reading it. That person wanted to clarify that EMR meant electronic medical record.
Okay.
Let's go to the next question. When studying a health condition that fluctuates over time, such as pain that may improve or worsen without treatment, the pattern of fluctuations may vary across individuals. How can we design a study that effectively accounts for both within individual variability and treatment effects?
Okay, that's where, no, I'll get too technical. You have like a mixed model to do that. So you're adjusting for the variability in subjects, within a subject and across subjects. And they don't have to be, you're right, they can go up and down. It doesn't have to be a pattern. You can have a linear effect like slopes if it's linear, to say, oh, is a slope in treatment 1 pain across time different than the average slope in 2. But if it's not linear, you can do polynomials, you can do quadratic, cubic, you can do splines. I'm talking like stat jargon, but there's different ways to model the outcome over time that's not linear. And when you get into the curvatures and things like that, you have to then look at specific times, because a spline is like a very wavy curve, a wavy line across time. So you may have to go in and say, okay, at 1 week post-treatment, do these things differ? Do these two groups differ? What about 2 weeks post-treatment? So you can look at different time points, because they may even cross in the future if there's some type of interaction over time. So long-winded way is say, yes, it can be done. There are sophisticated stat models can do that. I don't know what I'm stating here really answers the question. That I say, seek out a statistician and help them do it, because we can design studies that look at both individual changes and group changes.
One last question, Alan. By my estimate, you've probably consulted with over 1,000 investigators over your 20, 30 years here at Penn State. If you had to give one piece of advice to a new investigator, who doesn't have a strong research training background, what would you tell them?
I would say as a first research project.
Sure.
I say as a first research project, do a retrospective study. Don't dive into a prospective randomized clinical trial. In that, usually, a lot of the reasons for that is cost is a big thing. If you're just coming as a new researcher, you probably don't have the funds unless you come up with a big startup package, which you're not going to get as a new person. But prospective randomized trials are expensive, and they usually take a lot of subjects. So my advice would be do something retrospective, observational. The data is already collected. Again, there's time and expense there, because not everything is in the EMR system, electronic medical record. You still may have to go in and pull patient charts to actually abstract some data off of the charts themselves that's not in the EMR. And that can be a very time-consuming process. It may take 15 minutes to a half hour per chart to abstract it out or more. But it's still usually cheaper than a clinical trial. And also, it can be done faster. It can get your foot in the door to at least get a couple of quick publications on a retrospective to get a track record, to then go for a randomized control trial or a grant application using that. So I guess that would be my advice. Take data already collected as your first project come up with some good hypotheses and go from there.
So start simply.
Yes.
Okay. Alan, thank you so much. We're 1 minute over. Want to thank you again for sharing your vast experience and your insight. Great talk. And everyone, remember, please fill out the survey for us, and you will get a link to view this as well as the slides. So thanks again, Alan. Great talk.
Thank you. Bye.